Parametric methods. Having discussed how to make optimal decisions when the uncertainty is modeled using probabilities, we now see how we can estimate these probabilities from a given training set. We start with the parametric approach for classification and regression. We discuss the semi-parametric and non-parametric approaches in later chapters. We introduce bias variance dilemma and model selection methods for trading of model complexity and empirical error. Introduction. A statistic is any value that is calculated from a given sample. In statistical inferences, we make a decision using the information provided by a sample. Our first approach is a parametric, where we assume that the sample is drawn from some distribution that obeys a known model. For example, Gaussian. The advantage of the parametric approach is that the model is defined up to a small number of parameters. For example, mean variance, the sufficient statistics of the distribution. Once those parameters are estimated from the sample, the whole distribution is known. We estimate the parameters of the distribution from the given sample, plug in these estimates to the assumed model, and get an estimated distribution, which we then use to make a decision. The method we use to estimate the parameters of a distribution is maximum likelihood estimation. We also introduce a Bayesian estimation, which we will continue discussing in Chapter 14. We start with the density estimation, which is the general case of estimating p of x. We use this for classification, where the estimated densities are the class densities. The probability of x conditioning on Ci, and the probability of Ci to be able to calculate the posteriors, that is the probability of Ci conditioning on x, and make our decision. We then discuss the regression, where the estimated density is the probability of y conditioning on x. In this chapter, x is one-dimensional, and thus the densities are univariate. We generalize to the multivariate case in Chapter 5.